Welcome to everyone. This is a masterclass on Structure-Borne sound power, and it's funded by the UK Acoustics Network. So we're very grateful to Kirill Horoshenkov from UKAN, as well as the Institute of Acoustics, for supporting this. It's going to be a series of lectures and demonstrations, and it's the result of a collaboration between Hawley Acoustics, University of Salford, and the University of Liverpool. So from Hawley, we have Martin McNulty and Nicolesh Patel. From the University of Salford, we have Josh Meggitt and Andy Elliott. And from the University of Liverpool, we have Barry Gibbs, Gary Seifert, and Carl Hopkins. So my name is Carl Hopkins, and I'll chair the first two sessions on the Monday and the Wednesday, and Barry Gibbs will chair the session on the Friday. So the focus of this masterclass is on the assessment of structure-borne sound power from machinery or equipment that's installed in structures such as buildings, ships, trains, or cars. And the idea for the course was to try and focus on practitioners, but as well, we also wanted to give researchers an introduction to the topic. So we hope we've aimed at the right point. And for some of you, some of the principles will be very familiar. For others, they will be brand new. And we've tried to arrange it so that we not only have lectures introducing the theory, but we're going to have experimental demonstrations to try and illustrate the various points. So as I say, the course runs over 3 two-hour sessions this week. And today we're going to start with an introduction to structure-borne sound power through comparison with airborne sound power. And the idea of this is to introduce the underlying principles that you need to quantify structure-borne sound power from machinery or equipment. And then we're going to have a few demonstrations that will illustrate various aspects of force and vibration measurement. And from that, we're going to look at describing the structural dynamics of a source as well as a receiver. So the plan is that all the microphones are muted by Martin at the IOA. And so if you have any questions, please put them in the chat box. And I will try and pick them up at the end of a lecture rather than in the middle. The first lecture is pre-recorded by Josh Meggitt. So as I say, we're going to start with this lecture by Josh Meggitt, who's unfortunately busy at the moment, so it's pre-recorded, and it introduces the concept of structure-borne sound power through reference to airborne sound.
Okay, good afternoon and welcome to the first presentation of this webinar series, focusing on the prediction of structure-borne sound and vibration. My name is Joshua Meggitt. I am a lecturer from the University of Salford, and for the next 25 minutes or so, I will be talking to you about the prediction of structure-borne sound. In particular, we'll be focusing on how this differs from conventional airborne sound prediction. So unfortunately, I was not able to make this webinar in person, so this is a pre-recorded presentation, which means I won't be able to stop for any questions as I go. Luckily, Carl has kindly agreed to answer any questions after the presentation on my behalf. So with that, let's get started. Now, I think it makes sense to start by asking, the general question, what are we interested in? And I think whether you come from building acoustics, NVH, or product design, our interest is in predicting the vibroacoustic response in a complex structure due to one or more acoustic or vibration sources. Now, this complex structure could be, for example, a building, a vehicle, an aircraft, or whatever. Now, the focus of this webinar series is on the structure-borne aspect of this problem. And in this presentation, we will look at how this differs from the airborne problem. Now, what we mean by the structure-borne problem or structure-borne sound is the scenario where the main path of propagation between the noise source, for example, a piece of vibrating machinery, and a listener is through structural vibration. Whereas the airborne problem, this propagation occurs mainly through air. So whether we are interested in the airborne or the structure-borne case, we treat the prediction problem using a source path receiver model. For the airborne problem, this approach is well understood and dealt with routinely. First, we characterize the source by its acoustic strength or its sound power. Next, we formulate a transmission model that describes how sound propagates in the space considered. And then this model enables the prediction of a sound pressure level at some receiver point. Now, what about the structure-borne case? For example, suppose we have some machinery on top of a building. When this machinery operates, vibration is propagated through the building structure until it radiates into a room where it's heard by an occupant. Can we formulate an equivalent source path receiver model for this problem? The answer is yes, you can, but it's not quite as simple as for the airborne case. Now, before we attempt to understand the structure-borne problem, we need to consider the airborne problem in a little bit more detail. So how do we treat the airborne problem? The first step is to characterize the acoustic strength of the source. And we do this using a quantity that's known as its sound power. We then formulate a transmission model that relates the sound power to the sound pressure level in some space. Now, here are two typical examples that you might be familiar with. The first is for free field radiation, where you can see we have a 1 over r squared here to give us attenuation with distance. And this second example here, this is for radiation into a reverberant space. You can see we have the 1 over r squared, but it's accompanied by another term here, which accounts for the effect of the room. Now, there's something important to note about these two equations. They both use the same sound power level. What this means is that the sound power level is an independent property of the acoustic source. It doesn't change if you put the source in a different environment. That is to say, if you place the same acoustic source in a different room, it will have the same acoustic power. Now, this is a very useful property because it lets us predict the sound pressure level in a wide range of environments with minimal effort. All you need is to characterize the sound power and then develop an equation for the transmission in the environment that you're interested in. Now, what about the structure-borne case? Well, we will see shortly that this property of independence is the principal difference between airborne and structure-borne predictions. To see why this is the case, we first need to unpick the sound power in a little bit more detail. So in general, whether we're looking at acoustic or structural power, power describes the amount of energy that is transferred per unit time. We could define it as in this equation here, where F represents force and U represents velocity. Now, suppose we have some vibrating machinery that radiates noise. The sound power of this source is the total acoustic energy transferred over an enclosing surface per unit time. Now, we can express this total acoustic power as the integral over the surface of the machine, where F represents the force that the machine imparts on the air, and U is the particle velocity of the air. Now, this is equivalent to finding the power radiated by each small section of the source and then adding them together. Now, if we recall that force is just pressure times area, we can express this dq term in this form here, where we have dA, the small area, P, the pressure, times U, the particle velocity. Now, to make life a little easier, we can assume that we're dealing with plane waves. This gives us a nice simple relation between pressure and particle velocity, as in this bottom equation here. Now, if we plug this bottom equation into the one above, and then this one into the one above it, we get an expression for the sound power level in the following form. Now, we said before that the sound power is an independent property of the source. Now, what this means is that the term QA is the same irrespective of the surrounding environment. Now, it's easy to see why from this equation here. The term in this equation that describes the surrounding environment is this ρ0c. This is the characteristic impedance of air. So long as the source is radiating into air, the sound power level will always be the same. Hence, the sound power level is an independent source property. Now what about structural power? That is, the power transmitted into a receiver structure due to the vibration of the machine's connections. We can define structural power in the same way as before. Here, F represents the contact force between the machine and the receiver, and U is the velocity at this connection. Now here comes the important bit. The velocity of a vibration source will depend on what you attach it to. If you attach a machine to a large heavyweight structure, you'll generally get a smaller velocity than if it were a lightweight structure. So we can already see that structural power is not going to be an independent source property. The velocity of a coupled source-receiver structure is related to the applied force by the receiver structure's mobility, as in this equation here, where YR is the receiver mobility. Now if we substitute this velocity equation into the definition of structural power, we get the following equation. Structural power is equal to the receiver mobility times the squared force magnitude. Now let's go back and compare the airborne and structure-borne cases. On the left, we have the airborne case. The machine always radiates into air, so the sound power does not depend on the environment. This means it is an independent source property. Now on the right, we have the structure-borne case. Depending on the application, the machine might be connected to different receiving structures, for example a heavyweight or lightweight floor. Because the structural power depends on the receiver mobility, we will get a different level for these two cases. So structural power is not an independent source property. So a quick half-time summary. We've seen that the sound power of an acoustic source independently characterizes its operation. This means that we can use the sound power to predict the acoustic response in any environment. Structural power, on the other hand, depends on what the source is attached to. This means that we cannot use structural power to predict a vibroacoustic response. This is because the structural power depends on the application. What we would like to do is find a way of predicting the structural power based on quantities that do not change with the application. So in order to predict a vibroacoustic response for a structure, we need independent source and receiver properties, which describe the active and the passive behavior of the structure. Passive properties, for example, mobility, these describe how a structure vibrates when it's excited by a unit force. We can often predict mobilities and similar passive properties using simple analytical or numerical models. Active properties describe the operational behavior of a vibration source. These are typically much more complex than the passive properties, so we need to resort to measurement to obtain them. Now, over the next few slides, we'll introduce in a bit more detail some of the independent, passive, and active properties, and then we'll show how we can use these properties to predict structural power. So we'll start with passive properties. The passive properties of a structural element, say for example a concrete floor, can be characterized by their velocity response to a unit force excitation. This gives us the mobility of the structure. As you might have guessed, the mobility describes how mobile or how flexible a structure is. A high mobility means that the structure is flexible, and a low mobility means that the structure is stiff. The mobility is defined as in this equation here. It's simply the ratio of the resultant velocity to the applied force. Here, the subscripts I and J represent where the response is measured and where the force is applied. Also, this little condition here, this basically states that the velocity Vi is due to only the force at Fj. That is, no other forces are applied when we measure this velocity. Now, often when dealing with structural elements, you will also run into the notion of impedance. This is another passive property, and it's just the inverse of the mobility. It's defined with a similar looking equation like this. So it's important to note that a mobility can belong to different structural elements. For example, you can have the mobility of a receiver structure, you can have the mobility of a vibration source, or perhaps the mobility of the coupled assembly, where the source and the receiver are physically attached. It's typical to denote the structure to which the mobility belongs using a capitalized subscript, as shown here. Now, to obtain the mobility of a structure, we have a few different options. For simple structures, we can use analytical or numerical models. For more complex structures, we can use more complicated numerical methods, or we can resort to measurement. In the next presentation, Nicolesh will talk a little bit about using simple analytical models to get the mobility of floor and wall-like receiver structures. And I think on Wednesday, Andy Elliott will talk about types of source mobilities and how we can calculate those. Regarding the measurement of mobility, the team at Liverpool have put together a great set of demo videos showing the mobility measurement process or the procedure on some simple structures. And I believe Carl will show a couple of these after this presentation. Now, before we move on to active properties, I think it's probably useful just to see a couple example mobilities so we have an idea what they look like. So here on the left, we have two slightly different mass spring systems and their mobility curves. As you can see, we get the expected resonant curve of a single degree of freedom oscillator. On the right hand side, we have the mobilities of two slightly different plates. You can see these mobilities look quite complex with lots of resonant peaks. However, as Nicolesh will talk about later, it turns out that we can actually approximate these complex looking plate mobilities reasonably well using just a straight line. So that's enough about mobilities for now. We can move on to the active properties. Active quantities describe the operational behavior of a vibration source. Ideally, we want active quantities similar to sound power in that they are independent descriptors of the source's operation. For a vibration source, it turns out that there are two such quantities, the free velocity and the blocked force. The free velocity is defined as the velocity of the vibration source at its connection points when there are no external forces present. This means that the source is not attached to anything, so it's freely suspended and able to vibrate as it likes. The blocked force is defined as the force at the connection of the source when the velocity is constrained to be zero. This means that the contacts are rigidly constrained. So this is equivalent to the force present at the connection if the source was attached to, for example, an infinitely rigid test bench. Now you can see just from their definitions how neither of these two quantities depend on what the source is attached to. This makes them independent source descriptors. Now it just so happens that these two independent quantities, the blocked force and the free velocity, are related to one another by the source mobility, as in this equation here. Now to independently characterize a vibration source, we need to have at least two of these quantities. It doesn't matter which two, because the third can always be determined from this relation here. So, this is all well and good, but we're interested in predicting structural power. Well, it turns out that by using these invariant source properties, alongside some description of the receiver structure, we can predict structural power based on a particular application. So we're now at a stage where we can derive the structural power based on independent source and receiver properties. There are a few steps to get to the equation that we want. We start with the equation for structural power. Now, by recalling the definition of mobility, we can replace the force term by the inverse mobility and the velocity. Next, we replace both the velocity terms by this relation here. Now, we haven't covered this relation in this presentation. I believe Andy will cover it in some detail on Wednesday. It basically relates the blocked force of the vibration source to the velocity in the coupled assembly, and it does so using the coupled mobility, YC. Now, the penultimate step requires another unfamiliar relation. We can represent the coupled mobility, YC, in terms of the independent source and receiver mobilities, YS and YR. So those of you that are familiar with electrical circuits might notice that if you replace the mobility with 1 over the impedance, the equation that you end up with looks very similar to the equation that you get when you add electrical components in series. And indeed, there are some equivalences between connecting structural elements and connecting electrical components. Now finally, by bringing together the above equations and taking the real part, we get an expression for the structural power. You can see from this equation that if we know the source and the receiver mobility, and either the blocked force or the free velocity, we can predict the structural power. This power can then be combined with an appropriate transmission model and used to make a structure-borne sound prediction. Now importantly, here we have predicted the structural power based on independent source and receiver properties. This sort of prediction isn't required for an airborne sound power because airborne sound power is already an independent property of the source, whereas structural power is not. Okay, now just onto some concluding remarks. So we have seen that the sound power is an independent property of an acoustic source. It's the same no matter what environment the source is placed in. Structural power, however, depends on what you attach the source to, and this means that it's not an independent property. The fact that the structural power depends on the receiver means that we cannot use it to predict structure-borne sound and vibration. We need to predict the structural power on a case-by-case basis. This predicted power can then be used to make a vibroacoustic response prediction. We have seen that if we know the source's blocked force or free velocity and the source and receiver mobility, we can predict the structural power using independent properties. To do this, we derived the following equations. The structural power can then be combined with a transmission model to make vibroacoustic predictions. So the principal aim of this presentation has been to highlight the difference between airborne and structure-borne predictions, and also to introduce this method of predicting structural power based on blocked forces and free velocities. There are still some questions to be answered. In particular, where or how do we get the blocked force, the free velocity, and the mobilities. And also, how do we obtain the transmission model to predict sound and vibration levels using structural power? These questions will be addressed over the course of the next 2 webinars. So that's all from me. I think before we open up to any questions, perhaps Carl is going to show a couple of videos to demonstrate the measurement of mobility on some simple structures. And then after that, there'll be time for some questions before we move on to Nikolesh's presentation on receiver structures and some simple models for vibration transmission. So thank you for your attention.
Okay, well, feel free just to put something in the chat if you do have a question. But what we'll now do is try and build on Josh's presentation, because from Josh, we've seen that we really need to know these things called the source and the receiver mobilities. And one possibility is to measure these mobilities, and Josh indicated where that was needed. And the other is, of course, we could try and predict or estimate it. So what we're going to try and do now is have 2 demos. And we're going to try and give you more of a background in using, understanding and measuring mobility by going back to a very basic, simple lump mass. And then we're going to try and build on that to get closer to a more complex machine. So we'll start now with a demo by Gary, who's going to look at force and mobility measurement. And this demo will use the calibration of a force transducer to illustrate all the kind of relevant principles of mobility with a simple mass, and then we'll build on that afterwards to get closer towards a more complex piece of machinery. Okay, so Gary, I'll hand over to you.
Thank you, Carl. Can you hear me?
Yes.
Good, good. That's good. Okay, hello everyone. I'm Gary Seifert and I run the labs in the Acoustics Research Unit at Liverpool. So we've got a video here for you. I'm going to probably crash the system now by trying to share my screen because I'm old. Let's just see. There we go. Right. Okay, so this video, we're going to look at measurement setups and calibration using solid block, mention averaging and transforming accelerants to mobility, and then displaying mobility on a log-log scale and comparing mobility measurements with theory. I'm going to stop and start the video a few times, which is irritating, but it allows us to just look in some detail at what's being shown. So let's see if it'll start now. That looks hopeful. It's getting bigger. Okay, so I'm going to stop it there. So for mobility measurements, we need basically 2 transducers. One is a force transducer, and you can see that here it's attached to a hammer. So this is a force hammer. And we need the force hammer because we have to excite the structure. Now there's 2 ways of doing this. We can use an electrodynamic shaker. That's one way of doing it. There are problems there. It's more difficult to fix such a device to structures. So the force hammer allows quite an easy way to excite the structure and to measure the force into the structure. So you can see the force transducer is on the end of the hammer here. And also there is the tip of the hammer has a material on the end of it. And that material actually dictates the frequency range of the hammer. So if you have quite a soft tip, like a rubber tip, then you have a maximum frequency of sort of 500 hertz. This is the plastic tip, which goes up to 2 kilohertz, and you can have a steel tip, which goes up to 7 kilohertz. So once we've excited the structure, we need to measure its response, and we have a small accelerometer here that will do that. So let's move on. I think we're just going to zoom in here and see, yes, there they are. Okay, so we want now to try and put in sensitivities for these transducers, and for that we need a conditioning amplifier. The transducers themselves are piezoelectric, and so they both produce a charge that's proportional to the force of the acceleration. And that means that you do need signal conditioning in order to input the signals into the analyzer. So here we have a conditioning amplifier, and that allows us to go to the calibration charts for the force transducer and for the accelerometer, and to put the associated sensitivities in to the system. We can also change the frequency range on the conditioning amplifier, and we can change the gain for each channel. Now, because we've got two transducers, we have to have a minimum of a 2-channel analyzer. Most analyzers now have more than 2 channels, but you need at least 2 channels. So the output of the conditioning amplifier then goes into the front end of the analyzer. Here we have a 4-channel analyzer. We're only using the top 2 at the moment because we've got a force transducer and an accelerometer. And the analyzer is set to measure the transfer function between those 2 channels. And so the display that you probably can't see because it's too small is accelerance up this axis and frequency along this axis. Now we have a vibration calibrator here, so we can actually put the accelerometer onto this vibration calibrator, and it produces a known acceleration, very similar to calibrating a sound level meter with a known sound pressure level. So that allows us to calibrate the accelerometer. However, no such calibrator exists for the force transducer. And while we would hope that when we put the correct sensitivities into our conditioning amplifier, we would hope that we get the right answer, there is a way that we can check that the system is working as we would want it to. So here's a setup now. What we have here is a resiliently suspended mass, and there's a man in a nice shirt. He's putting on an accelerometer using beeswax onto the back face of the mass. So what we have here is actually is from Newton. We have force, we have mass, we have acceleration, and force equals mass times acceleration. Now, because of the way we've set up the analyzer, the reference quantity is force, and so we have acceleration over force, which is a quantity known as accelerance. And we can work out, if we rearrange the equation, that that's actually equal to 1 over the mass. So let's just have a look at the there's a man hitting a mass. Now, you'll notice that there are several hits in acoustics. As you know, when you do building acoustics or whatever, you're measuring sound pressure levels. You don't measure at one position, you measure an average quantity, an average sound pressure level. And it's exactly the same with structural measurements. You want to do an average, so we'll hit the block 5 times. And we're zooming in now. Okay, so here's the analyzer screen now. So we have accelerance here, and we have the quantity that's being measured. And you can see as we hit the block, may not be exactly in time, you can see the number of averages here increase. So each time the blocks hit, the transfer function plot is updating. So that's a plot of linear accelerance, but we can log that axis. Where is it? Come on, there it is. Okay, so we're going to log that axis now. And you can see we get a straight line, which is actually 1 over the mass. The mass, if you've noticed, was 3.85 kilograms. And the 1 over the mass should be the accelerance, which is this value up here, which I can't read. which is something like 2.259 meters per second squared per Newton. Okay, so if we've done this procedure, we're now convinced ourselves that the acceleration and the force are being measured correctly, that the signals are being conditioned correctly, and that we've got confidence in the measurement system. So we use a simple mass, because when we go on to do more complicated structures, it may not be obvious what the response is going to be. Now, in Josh's excellent presentation, he mentioned the term mobility. And so what we're measuring at the moment is a thing called accelerance, which is the acceleration over the force, but mobility is what we're really interested in. And that is the velocity over the force. And so what we ask the analyzer to do is to integrate the acceleration channel. And if we do that, we should get the mobility of the block. So let's have a look at that result now. Again, we're averaging. Okay, so what we've got there, it's quite a simple plot, but it makes much more sense actually if we log both axes. So we're going to see the analyzer now log the y and the x-axis. So we've now got mobility on the y-axis. Yes, that's right. So let's see that. Log, there we go. And if we do the second log button, so now you can see we've got a classic straight line mobility that is decreasing as frequency increases. And so this is a standard sort of mobility plot for a mass. And we can actually export those results into spreadsheet and do a prediction. And we can compare measured results with predicted results, which should appear in a moment. And there it is. So you can see there's very good agreement between the predicted and the measured results. And we're actually plotting now the velocity over the force, or 1 over j omega, the mass. And that's all I've got to say about that. So if I can stop sharing my screen and hand back to Carl.
Okay, thank you, Gary. Okay, so Gary's run through the calibration of a force transducer, because we're going to try and build on that in a moment, but also that we're aware that whilst many people calibrate microphones and calibrate accelerometers, perhaps they don't come across force transducers so often. So if anyone's got a question, please feel free to ask. Okay, if not, then we'll move on and we'll go to the second demo. Okay, let me share my screen. Okay, hopefully you can now see the next video. Now, this is a very nice idea that came from Barry Gibbs for this. And so what we're going to do is build on what we've just seen about the mobility of a simple mass. And we're going to try and use that to consider how it could help us understand a more complex piece of machinery, which we're often going to be interested in. And you'll remember from that first video that we need that source mobility. So we're going to build on that last idea of the mobility of a simple lump mass. And to extend this, we're going to attach a piece of metal so that we have a cantilever that could represent the fixing point on the machine. And that will allow us to measure the mobility and consider the mobility in terms of mass-like, spring-like, and resonance behavior. And we're then going to look at measuring the source mobility of a compact pump at its different mount points. So let's just have a quick look at that pump, which is what we're trying to measure the source mobility. So here's an image of that source pump from different angles. So the fixing points are down here. There's 2 on each side. So from underneath, 1, 2, 3, 4. And so you would bolt this fairly compact pump onto some kind of structure. This came from a project in which Barry Gibbs, Andy Elliott and Josh Meggitt and Gary Seifert and myself from Liverpool and Salford, we got together and did some work with Boeing. And so it's a pump that's installed in an aircraft. But what we're interested in is that source mobility at each of these fixing points. And what we realize is we've got a very seemingly complicated piece of machinery. The housing hides all the internal components, but we know that it's sort of, well, there is possibly a line of symmetry, but it's asymmetric down this point. So we would expect perhaps different response at the different pairs of fixing points. So this is what we want to move towards, and we realize that we've got a very complicated piece of machinery. And what we will want to do is to measure the source mobility. So following on from Gary's measurement there, just again, we've got the force hammer, and at a fixing point here, we've got an accelerometer. So Gary's hitting it from below. And as before, of course, we average several times. Oops. And here you can sort of just see through the grill. So we're aware that we have a very complex inside, that the housing hides all of these internal components. But what we want to do is say, okay, we have a very complex machine here, but actually when you're considering structural dynamics at low frequencies, it's often possible to represent fairly complex structures by a combination of a few masses, springs, and dampers. So on the basis that this machine might be considered as a kind of lump mass here, we'll return to take some more measurements on that calibration mass that Gary showed you. And then we're going to modify it under Barry's suggestion of adding a small cantilever to represent these kind of fixing points. So we return to the calibration mass. So here's that cylindrical mass from before that Gary used to calibrate the force transducer. And this time we've got a thin strip of metal that's bolted in the center. The accelerometer is fixed on that outer edge as if it was a fixing point on the edge of the compact pump. And then Gary is going to hit just opposite the fixing point of that accelerometer there. So as before, we take several averages, and because it's rocking a lot now, so after each measurement has to be steadied to make sure it's stationary before we do the next one. Okay, so here we have the results, the measured mobility of that cylindrical mass with that strip acting as a cantilever, and we're measuring on the outer edge. Now, thinking back to what you saw with Gary's calibration before, when we just looked at the simple lump mass, we just had a straight line. So the first thing that strikes you is that, yes, this mobility curve is more complex. We don't just have a single gradient slope anymore, but there are features that we can relate to it. And the first one is in this low frequency region here, where we have more or less straight line mass-like behavior, where the mobility is proportional to 1 over the frequency. So despite the fact that it's very complicated at low frequencies, it still behaves pretty much like a mass. We then have a kind of anti-resonance, so a dip in the mobility. And above the anti-resonance, we have spring-like behavior where the mobility is proportional to frequency. So we have a rising slope here. So we've got a mass-like behavior, an anti-resonance, spring-like behavior, and then we hit the first resonance because you can envisage a half wavelength on that cantilever between the fixing point and the edge of the cantilever. And at a resonance, remember we're measuring mobility, which is the ratio of velocity to force. So at resonance, we have a high response, a high velocity, which gives us this peak here. So we're able to describe features, a mass-controlled region, a stiffness-controlled region, and a resonance region. So now we're going to return to that compact pump, and measure the driving point mobility at one of these fixing points. So as before, averaging several times. This is that resilient suspension that Jost mentioned during his talk. It's a setup we would use if we were measuring free velocity as well, on if the pump was actually in action. But here it's unplugged, it's a passive element, and Gary's measuring the driving point mobility at the fixing point. Okay, so when we plot up the results from that measurement, we see that we have something very similar to what we saw before. There's a low frequency region where, despite the complexity of that pump, it's just acting like a large mass, with the mobility being proportional to 1 over frequency. So there's a mass controlled region here. Then, just like we had with our cantilever on that simple mass, there's an anti-resonance, and above that, we have a stiffness controlled region where we have spring-like behavior and the mobility is proportional to frequency. So here, when we measure mobility, it's complex. And so what we're showing here is the magnitude as the solid black line, and the real part, which is a red line, which actually down here, of course, as its mass control behavior, they're nominally identical. So right the way up to 2000 Hertz, even though we have an incredibly complicated looking machine, actually it's sort of approximated by sort of lump mass behavior and lump spring behavior. So this just sort of reminds us of the potential to use very simple models to try and explain rather complicated devices. Now, we mentioned before that there are 4 fixing points. So here are measurements of the driving point mobility at each of those 4. Now they come in pairs, and Barry has prepared this graph. And so you'll remember that there was one line of symmetry, but the 2 pairs of points you would expect to be slightly different, each pair to be slightly different, because they're a different distance probably from the center of mass of that pump. So we have mass controlled region down at low frequencies, but there's a slight separation between the curves because those fixing points are a different distance from the center of mass. There's an anti-resonance, then there's a stiffness controlled region, depending on the fixing and the thickness of the metal and the material properties of the metal. And then we start to have resonances above 2 kilohertz. We didn't see that on the last slide, but we see it now. Those resonances occur on those cantilever fixing points. But actually the dashed green line gives an indication that if we just treated those cantilever fixing points as a simple beam, then we could estimate the mobility as we do with this green line, and we get a very rough approximation of what we would expect there. So in this demo, we've taken a simple mass and made a slight modification to show that the structural dynamics of a seemingly complex piece of equipment can sometimes be approximated by a combination of masses, springs, and dampers, with consideration of these resonances at higher frequencies. And this principle not only applies to the source mobility of machinery and equipment, but also to some receiver structures to which they're fixed. So in the next lecture, Nicholas Patil will look at receiver structures in more detail. And this is because we not only need to know the source mobility, but we need to know the receiver mobility. So that's the mobility of the structure to which this machine is connected. So I'll just stop sharing my screen and then look at the questions. Okay. Okay, so there's a question on the number of averages to be taken. And as you probably saw on the video, for the lump mass itself, it doesn't vary very much. Once you get to a certain number of averages, you see that the curve is just not changing. So probably for a calibration mass, you probably only need to hit it about 5 times. Some people probably only hit it 3 times. But for a more complicated structure where perhaps you're a little bit more worried about the angle of your force hammer and things, you might do it more times than that. Of course, you're keeping an eye on the coherence to try and make sure that you have data that's free of noise. Okay, there's a question from Claudia. In the measured data, there was a slight kink about 1000 Hertz, which was absent from the prediction. Was there any significance to that? 1000 Hertz. Okay, I think, I suppose the answer to that is that we are idealizing a very complicated source and pretending that we can just model it as a very simple connection of springs and masses, and in reality it is much more complicated than that. So that kink in the curve is most likely to be the fact that there is some kind of internal resonance or something that is not accounted for by that very simple model. And there's a question on the mounting points are not the only connection between source and structure. How do you deal with pipes attachment to the pump compressor? At this point, I will ask that question to either Andy Elliott or Barry Gibbs, whichever wants to take it.
Hi, Carl. I'm quite happy to take it. As Josh Meggett said, that a source is defined by where it's attached. So if it's attached through extended components like service pipes or fuel pipes or waste pipes taking away gases and things like that, you have to treat that as a source as well. And the same principles apply. So for we found in buildings where there's water services, where the pipework can go throughout a high-rise building, we have to treat the source in each room almost separately in terms of its activity, either its block force or free velocity, and the mobilities at those contact points. It sounds long-winded, but it is relatively straightforward.
So thanks, that was a good question. It's just a reminder of actually, yes, the real world is much more complicated and you do have to consider power injection at several points. And it's not only just several points on the same wall, for example. It could be that some of the mounting points are on the wall and some of them are on the on a floor. So yes, you might have a boiler or something where the boiler is mounted on one wall, but actually the fixing points on the pipework are not only on that wall, but on adjacent walls as well. And later on, of course, we're going to look at how you propagate the structure-borne sound power through a structure. And at that point, you have to be aware that you are injecting power from vibrating machinery, often on more than one wall or floor. Okay, are there any other queries? So far what we've done is we've had our introduction to structure-borne sound power, looked at why it's more complicated than airborne sound power. We've looked at the calibration of a force transducer to introduce the idea of the mobility of a simple lump mass. And then we've tried to extend that to show you that actually, even when you have a complicated piece of machinery, sometimes in the frequency range you may be particularly interested in, which is down at low frequencies, you can treat fairly complex pieces of machinery still as a combination of lump masses and springs. Okay, so the next point is to move on to Nicolesh, who will now talk us through receiver structures, because you'll remember from the first presentation that we also need the receiver mobility. Okay, Nicolesh, can I hand over to you?
Yes, thanks, Carl. So can someone let me know if they can see my screen?
Yeah, that's okay.
Yep. Perfect. Okay, so the next session, as we saw in the first session, to have a complete sort of characterization of your structure-borne sound or structure-borne response, vibration response, you not only need the source parts, but you also need a characterization of the receiver assembly as well. So this presentation, I'll be focusing on the receiver structures, the prediction and measurement. So just a quick background about me. I'm an acoustics engineer in the vibration group at Holy, and we sort of collaborated with University of Salford and Liverpool to sort of do these UKAN sessions. Okay, so let's move on to the main content. Okay, so before I start the presentation, just a brief overview of the topics that we'll see. So just a brief introduction on what a receiver structure is, what kind of receiver structures we might see in buildings, and how do we account for receiver structures, like what's to understand that, like what is the effect on the power transmitted or the injected power into the structure. We'll then look at some simplistic sort of functions or relationships to see if we can predict the receiver mobility without going through a big measurement campaign or exercise. And we'll also touch upon the measurements. And at the end, we'll follow up with some demos on real receiver structures in buildings and see how well sort of they compare with the existing theories or relationships that we have. Okay. All right. So what is a receiver? So typically we'll have a dynamic source and receiver assembly. So your source will be the active part, which will generate some sort of combinations of forces or moments and importing structure, which is what we call as the receiver. Now, important thing to note is that the receiver itself is not an active part. Receiver is a passive component of the assembly, which is excited by the source. Okay, so as an example, in buildings, you might have, let's say, a pump or a chiller directly placed on the slab. So the plant item will be a source, and the plant sort of deck or the slab, that itself will be the receiver structure. As we saw in sources, you can have a structure-borne source or airborne source. Similarly, your receiver can also be either like a structural or a sort of solid, example like a wall or a slab, or you can have a fluid medium as a receiver. So you can have an air cavity itself acting as a receiver. In buildings, what we most commonly see, the structural shape and form usually conforms to plate type structures or a ribbed plate type of structures. So these kind of receiver structures, which take the form of plate or a ribbed plate kind of construction, they are the most common receivers in buildings as far as we're concerned. And to characterize a receiver, just because it doesn't have an active component to it, the passive property, which can be used for an independent characterization, is the receiver mobility, or you can have a receiver impedance or receiver dynamic stiffness, which are sort of relatable to each other. Okay, moving on. Just to give you a brief outlook of the range of receivers that you may have in the world. So in buildings, as I just mentioned, you may have a very simplistic plate type construction, shape or form, rectangular, square, kind of plates, very simplistic sort of construction. And in the other world, let's say, if you just take the case of an automotive sort of industry, you may have sources and receivers of varied size, shape, and forms, some of them which can't be easily generalized, for which you may just be needing very discrete measurement or discrete simulation. So to give you an overview, you can have a range of different receiver structures which may not be just governed by any sort of general shape or forms. They can take any form depending on application. For buildings, we're concerned with mostly plate type receivers. Okay. All right. So how do receivers affect the power, or why do we need to account for receivers? So going back to the equation for transmitted power that we saw in the earlier presentation, the transmitted power, or the sort of the injected power in the substructure, which is the receiver structure, is not only governed by the source properties, which is the source mobility or the free velocity or the block force, but it's also governed by the receiver mobilities. So if you can see the highlighted terms, YR, that's the receiver mobility that will be counted in the injected power or the transmitted power. Now, everything can be traced back to power. So if you wanted to make a prediction, or if you wanted to understand how a receiver might produce a response, whether a airborne like a noise response or a vibration response, we need to understand first how much power has been going into the receiver. So to also, like, maybe if you wanted to know what kind of isolator you may need to isolate a source on a existing sort of plant slab or something, you may want to know what the source structure is doing, but you also want to know what the receiver structure is doing to understand and make a appropriate selection of whatever mitigation you want to use. So in all, what you need is you need to know what the receiver structure is doing, what is the characteristic of the receiver in terms of mobility. And then once you know the mobility of the receiver, you can start to utilize it with your source terms and isolator terms and make a prediction of power and go from power to, look at what kind of response you can get and what kind of isolator you need, static deflection, etc., etc. As a quick example, so on the right-hand side, the graph you will see is just like a simulated example of a a transient drop on two different slabs. So one is 150 mil concrete, one is a 14 millimeter timber. And just to show, these are two different structures which are characterized by different receiver mobilities. And you can clearly see the power injected in each differs in the frequency range. And this is because the receiver mobilities in the frequency range of each structures is different. So the point to take is you need to use or sort of account for the receiver structure through its mobility or through knowing its characteristics. Okay, moving on. More effect on the power. If we also see, like, at some extremes, let's say, whether you have a source mobility very, very less than the receiver mobility, or whether you have a source mobility far, far greater than your receiver mobility, you get these sort of approximate equations for the injected power. And you can still see you cannot take the effect out of the receiver mobility from the power injected relationship. So the key point here is whether you have your source mobility very high or low relative to receiver mobility, don't just ignore it. You'll have to still make a check or just account for it using these equations that you have. So you can't ignore the effect of the receiver in a general case or either in an extreme case. The only caveat to that would be if you had a completely rigid receiver where your source mobility, where your receiver mobility is zero, in which case the power injected will be zero or negligible. So, and in realistic cases, unless it's a very, very thick ground bearing slab, you would still have some degree of receiver mobility that you would need to account for. Okay, moving on. Isolator selection. So, like power into receiver structure coming from a source directly coupled to the receiver, if you had a isolated source, you also need to, you'll still have some power transmission into the receiver. And this equation, the first equation that's there, that governs the power that goes into the receiver when you also have an isolator in your assembly. So the term YI sort of refers to the mobility of the isolator, which would be sort of mobility of a kind of spring element. Okay, and from that equation, and using the previous equation, which didn't have the term yi, you can get to a simplified sort of insertion loss equation, which is dependent on the mobilities of the source and the isolator and the receiver. Now, if you were to think of a completely mass on spring case, you have like established relationships for transmissibility, and you always see a mass on spring diagram. The base is always rigid. It always shows that the receiver is rigid, but in reality, these bases are not rigid. For example, suspended plant slabs, you get these suspended plant slabs, they won't be rigid, so you will have some effect of the receiver mobility. And if you look at the insertion loss equation, if it was perfectly rigid receiver, the insertion loss would totally just depend on the isolator mobility and the source mobility. But if you have a receiver as well, a mobile receiver, what you would want to do is have your isolator mobility as high compared to the receiver mobility, so as you are trying to approximate a spring on a rigid base sort of scenario. So on the right-hand side, you'll see a table. So if you just look at the first 3 entries, you have a source of some mobility installed on a concrete floor, a timber joist floor, and a joist floor installed on the bay between the joists. So you can see in the first 3 entries, the source mobility remains the same, the isolator mobilities remains the same as well. But when you look at the receiver mobility, obviously, because we have a different construction of the floor, you get different receiver mobilities. So the concrete floor has the lowest mobility, and in between the bay, between the joists, you have the highest mobility. And you can see as you move away from that rigid base approximation, which is going from the concrete floor to the bay between joists, you'll see the isolator insertion loss that you would start to see decreases. It's because your receiver is now becoming more mobile, and that's in a way you're not getting your isolation efficiency. So the point here as well is that even if you have an isolated source, it's not just totally dependent on, okay, I've looked at the source, I've isolated it, everything will be okay. No, you also need to account for, or at least have a check on what your receiver structure is. If it's very mobile, suspended slab, you might need to upgrade your isolator selections, such as to have that sort of difference between your isolator mobility and receiver mobility. Okay, let's move on. Okay, so in buildings, as we discussed, we're going to have some floor, slab, and walls, typical receivers for any structure-borne mechanical plant sources that will excite them. And how can we now sort of measure or predict or account for the mobility of these receivers? So depending on sort of what you can do, you basically have 2 approaches available. So one is a predictive approach or an engineering approach, and then you might have a more precision approach where you do like discrete measurements, account for the real world dynamics on the on-site construction. But it all depends on basically what you have to hand. Sometimes the scheme may not be built, you may not have access to the site, you can't do that, in which case you want to look at some predictive capabilities. But if you have the site built, you can go and measure on the site itself what the mobility of the plant slab is going to be like, but you still want to look for if you have the adequate capabilities. Do you have the right do you have the right mechanisms for analysis? Do you know what kind of systems you will need? And also, how critical is your overall sort of end prediction? Is it a very critical facility, or is it a general sort of facility where the responses or the criteria is not as critical? So all these factors sort of amount into whether your decision to whether you want to go through a predictive route or do you want to go through a measurement-based route. Okay, moving on. So let's start with the prediction approaches. So to acknowledge, firstly, in buildings, you might have a sort of a heavyweight receivers, masonry wall, concrete slabs, or you may have like a lightweight construction, a timber joist floor, thin CLT floor. And when you want to do these predictive sort of approach is, let's say, obviously, if the scheme is not built, you may not know where exactly the source is going to go, or you just can't measure it because you don't have the capability or the resources. Now, the difficulties generally with the prediction approach, if you account for the previous points, is that you may not exactly know where your plant is going to go, where your source is going to go, because you maybe are in the early stages of your design. And if you want to do like a full-scale prediction approach using like finite element and all that kind of approaches, it might get expensive. You may not have the right sort of resources. So our goal is, can we use the existing information that we have and still have some sort of simplistic sort of prediction or simplistic model to sort of predict the behavior, or let's say the average behavior of your receiver? Okay, so in your prediction approach, so first thing, let's say we want to do like a simplistic prediction. So the first point, what we can do is, because we have a plate-like receiver, we can see if we can utilize any sort of infinite plate kind of approaches to represent the behavior of your finite plate. So let's say you had that finite plate in the earlier slide, and you just assume that you have an infinite plate of the same thickness now. So because you can use an infinite plate approximation, you have these ready-made relationships based on some material properties and the thickness of the slab to get the characteristic mobility, which is the mobility of the infinite plate of same thickness. So we, as a starting point, we can use those relations to establish a mobility of the plate. And theoretically, there has been relationships which have been developed to sort of establish also what are the maximum bounds or minimum bounds of the mobility for that kind of construction. So you're not only looking at just like a simplistic behavior, but you can also sort of put a bound on it to what maximum can it go, what minimum. Okay, to demonstrate this, we have got here relationships laid out. So characteristic mobility given by Y car, and you've called the maximum and minimum bounds. So if you want to dig deeper into these relationships, there's a good paper which I have sort of reference to below the table, calculation of mean and maximum mobility floors by Andy Moorhouse and Barry Gibbs. So that has some good sort of explanation on the relationships, how they are derived. If you sort of want to see how they sort of match to a finite plate mobility. So I've done like a little simulation based on the utilizing the characteristic mobility for a 200 mil thick concrete plate and compared that to a finite plate of the same thickness, but a finite bound 5 meters by 6 meters. And so I've looked at around 50 random points on the concrete slabs, simply supported slab. So these are the results of the absolute slab mobility that you get. So what you've got in gray are the different sort of mobility measured at different points on the concrete slab, and in the red in the middle that passes in the red curve that passes through the middle, that's the characteristic mobility of the infinite plate of the same thickness. And in blue, what you have got are the maximum and minimum bounds of the mobility. Also, what I've just shown here is an important aspect, what you can sort of get from your mobility as well sometimes is you can also get a good prediction or good measurement of your natural frequencies of the plate or the slab that you're looking at. So if you measured your mobility or you modeled, you can also get the natural frequencies from it. So originally what we can see here now is the characteristic mobility sort of represents sort of the average, goes through the middle of all of these mobilities, and the blue curves represent the maximum minimum mobility. So to establish sort of what can be the worst case or just like the very least worst case. Now, as building consultants, we like to see everything in 1/3 octaves more than narrowband. So converting that to 1/3 octaves, you get this plot, and the black line, that's like an average mobility of all the mobilities that I have just randomly chosen. Now you can see that average mobility curve matches very well with the characteristic mobility. That's the red curve, and this is to show the power of utilizing the characteristic mobility of just an infinite plate using a very simple relationship to sort of characterize the actual receiver, for which you may have very limited data on, or you may not be able to measure. So it's a very, very good tool, and you can see the predictions for this slab are of the averaged, let's say, is well within sort of 10 dB of the characteristic mobility. So we can say sort of the characteristic mobility of an infinite plate is sort of very well sort of suited to representing sort of the averaged behavior of your receiver. Okay, similarly, because we had a real part of the receiver mobility term in the equations as well, you've got the real mobility as well plotted. Very similar sort of behavior here as well. And when you also look at the averaged curve, also looks very, very good compared to the infinite plate mobility. So all in all, I think with very limited information available, if you just know the thickness of the slab and the, what material it is, you can just use the characteristic mobility of an infinite plate as a very good starting point to sort of account for your structure or use within your any predictions or any sort of initial guideline advice. Okay. Okay. Likewise, now we have, let's say, lightweight receivers as well. Now, these are not as same as construction as a concrete slab, which is like a homogeneous construction. Generally, in a lightweight receiver, you will have let's say, a timber joist floor. You will have some bays, which is the area between the ribs or the joists. So in this case, what you have two sort of different constructions in essence, or two different shapes, which is the bays and the ribs. So in the bay, which is sort of like a plate-like structure, you can represent the mobility by using the infinite plate mobility, as we just discussed in the previous slide. And for joists, you can treat that as like an infinite sort of beam. So you just use this infinite beam characteristic mobility relationship to get the sort of the initial sort of value of the mobility of the joists. Okay, so as simple as that. You just use where your location is. You use the appropriate mobility relationship. Okay, so this is just one example now for a real timber joist floor that was recently measured. Now, at initial glance, it does look a bit messy, and it does look like slightly variable. But if you see, at least in the bay area, which is the right-hand side plot, if you have some sort of average behavior, you can sort of have like a straight line at about 1 × 10⁻³ meter per second Newton. And on the left-hand side over joist, that's a bit sort of messy, but it lies generally between 1 e⁻³ and 1 e⁻⁴. And we'll talk about this a bit more in detail. So if you go next slide. So this is also some more data of 15 different timber constructions, timber floor constructions at multiple locations on each sort of timber floor. And you can see there's also like a heavy sort of variance of the what the actual mobility of the different floors are. But if you were to do like an averaged value, you would see that the average generally lies in about sort of 1 e⁻³ meter per second Newton. And what you can do is you can sort of assume this when there's sort of no other information available. So because this is based on extensive sort of test data that has been measured all over in various timber constructions. Okay, and what has led to a development of is some sort of a mobility master curve for these kind of ribbed plate structures. So what you have here is a normalized mobility. So you've got a measured mobility compared to the infinite plate mobility, and on the x-axis you've got the distance to the bending wavelength from the joist. Okay, and you can see as for most of the constructions, you can see when you normalize the measured mobility to the infinite plate mobility, you sort of get this 1 e to power minus 3 or 10 to power minus 3 meter per second Newton sort of general characteristic mobility. So it sort of is a development, or it sort of is a initial sort of proof or guiding point that we can use a 10 to power minus 3 meter per second Newton value for your timber joist floor when you are going further from the joist, which is if you are in the bay. And for ribs, generally, you can sort of use a value of 10 to power minus 4. Now, these are obviously, there's an acknowledgement here that these are very generalized sort of relationships or generalized values, but it's a good starting point to use within your predictions. And if you want to go into more detail, you can do your own sort of measurements and more survey to get the sort of more appropriate mobility. Okay, all right. So that was all about predictions. So let's talk in brief quickly about measurements. So when you're looking at measurements, obviously, it's not just a simple case of if mobility is just velocity over force. It's not a simple case of just measuring some velocity and measuring applied force and dividing one by the other, and you'd get the right mobility function. So firstly, you need to consider that proper characterization will involve part measurement and part analysis. So the analysis itself is as important as your measurement. So for measurement, you'll require the right setup, the right sensors, you'll require quiet conditions, and you might require some multi-channel analyzers, simplistic, some class 1, class 2 vibration level meters may not have the right functions, may not have the right capability to use that. And for the analysis, it's not a simple 1/3 octave analysis. You need to use a transfer function analysis given by H1 or H2, which utilizes the sort of the cross spectrum and the auto spectrum of the velocity and the force terms. And through that, you get the eventual mobility. And to see if you've got the right sort of measured mobility, you can just compare it to the characteristic mobility of that sort of floor, and it should just sort of go up through it or around the midway of that sort of mobility curve. Okay, some measurement tips. If you have a big sort of very big sort of area, and if you wanted to measure some transfer mobilities, you can use principle of reciprocity, where if you have two different locations, applying force at one location and measuring velocity at other location, that will be the same at applying the force at second location, measuring the velocity at first. So the transfer mobilities are reciprocal. If your sort of slab is generally sort of a rectangular shape, and if you are at symmetric points, you can just assume that the mobility is sort of equivalent at the symmetric points because of a homogeneous construction and equal sort of distances from the boundaries. Lastly, you can sort of have a sort of a engineered approach or a statistical approach, because let's say in a case, if you don't know where the plant is going to go, and if you don't want to use predictions, you can measure mobility at a few points and get some measure of the average mobility. Or if you want to, or if you have to predict very accurately where the source is going to go and where the receiver how the receiver will behave, you need to separately measure at each sort of contact point and put that in a matrix and use it with the source information to get some sort of prediction of what the vibroacoustic response will be. Okay, all right, so we had a quick look at all the predictive sort of techniques and briefly on the measurements, what we need to sort of account for. To conclude then, so receiver structures are your passive part of your dynamic source receiver assembly. These will affect the injected power, the response that you get into your receiver or sort of any cavity, and sort of what isolation you need to use on your source. The characterization is therefore important. You need to either use simplistic predictions based on characteristic mobility functions, and this may be a good representation of the average behavior, or you may need some measurements if you need to dig deeper in some critical cases, depending on your precision needed. But if you're doing measurements, make sure that you have the adequate capability, you know what kind of analysis you need and what kind of instrumentation you will need. Okay, so before I move to demos, I'll just quickly check if there are any questions. Okay, doesn't look like there are any questions at the moment, so I will share my screen back. Okay, all right. Can everyone see my screen again?
Yeah.
Yeah, okay. All right. So what we've got here for the demos, we've got some measurements on a sort of a heavyweight, sort of thick wall, and we've got some measurements on a lightweight structure. Okay, so I'm going to play the videos for thick wall. First, it's a brick wall, and it will show how the measurements are sort of done, and then we'll see what the actual results look like. Okay. So you've got an accelerometer on a brick wall fixed via beeswax. You can also use super glue if you don't have beeswax, and an instrumented hammer tapping right next to the accelerometer to get the sort of driving point or the point mobility. You may need to sort of do 3 to 4 hits to get a sort of averaged sort of mobility at that point. Okay, so these are the results of the brick wall that we just measured. So what you've got a black line, which is the brick wall mobility magnitude. So the absolute mobility of the brick wall receiver. You've got the dashed red, which is the real part of that mobility. And in dashed, you have got the characteristic mobility of that sort of brick wall based on whatever the material properties and the thickness of the wall were. And you can still see just for that, for this kind of realistic structure as well, you are not far off by just using a characteristic mobility, especially knowing how much you may need to do if you want to go by the measurement route. So the characteristic mobility of this brick wall matches quite well if you were to think about of the average sort of response in that sort of frequency region. If you like to draw sort of an averaged line of across that mobility curve, it would match quite closely with the characteristic mobility curve. And also the differences are not that high. They're well within a decade. So they're around about in the region of 1 e to power minus 5, the measured and the characteristic mobility. So this is a really sort of powerful example of how you can just consider like or use your characteristic mobility as a powerful sort of tool in your predictions or in your design for any kind of purpose related to structure-borne noise prediction or vibration prediction. Okay, so moving on. We've also got some sort of historical sort of measurements that have been done on sort of actual structures. So these are just concrete plates and also some E-rated concrete plates on the right. So in both cases, you'll still see, if you were to sort of represent the sort of averaged behavior, you've got the characteristic mobility, which sort of very nicely sort of fits in through the average sort of average view of the mobility plots, but as well, if you want to maybe consider what kind of worst case could it have, you can also look at the maximum and minimum bounds, which are also very simplistic relationships, which you can use. Let's say if you wanted to have a conservative sort of estimate of what your floor can do, maybe you can use a sort of a characteristic, a maximum and minimum mobility bound equations, or if you're just interested in the averaged sort of behavior of the plate, you can just use the characteristic mobility. Okay, so the next one we have is a demonstration of mobility of a joist floor. So let's have a look at the video. Okay, so as you can see, you need like a proper setup when you're doing a mobility measurements with your analyzer, as well as your force hammer and the accelerometers. So this is a timber joist floor. As you can see, you've got the bays in between the joists, and you've got some positions in a grid marked on top of the timber joist floor. Again, similar technique. Do take an average 3 to 4 times, 3 to 4 hits. This shows sort of in close-up how close you need to be to the accelerometer. You can also do measurements either side of the accelerometer and then average those. That's over the rib. One thing to also note is in some cases, if you have a, let's say if you're doing your measurement on a ground bearing slab, if you wanted to know the mobility of a very stiff structure, you may need to have also a very heavier force hammer. So the hammers that we just saw weren't very are applicable to maybe lightweight structures, or a suspended slab even may do in certain cases, but you may need to have like a sledgehammer, like an instrumented sledgehammer, to impart some sort of response or some sort of force into the structure for a proper measurement. Okay, so moving on. So these are the measurements that we have got from the video that we just saw. The mobility over the joist and mobility in the bay. And as we sort of also, as I also stated earlier, it does look variant, and we have sort of established from many measurements over sort of the ones available in literature that there is a variation in different timber constructions. But if you were to look at the averaged mobility across different constructions, it generally tends to be about 1 × 10⁻³ And if you were to take the measurements and also sort of normalize them to their characteristic mobility, you sort of get a much more clearer picture that your measured mobility should be around 1 × 10⁻³ meter/second. And also at the ribs, you generally see a behavior that you get a mobility value of about 10⁻⁴. So this mobility master curve for rib plate structures is quite useful, because this also sort of helps you to use them in your sort of initial sort of design or predictions in absence of any sort of measurement or sort of a thorough prediction sort of exercise. So you can use these as a starting point, and if you want to go deeper and you want to take your own measurements, you can take your measurements, but you may still find that eventually the average sort of behavior or average mobility that you find does lie in this region. For the base, generally in 1 e to the power minus 3, and for the ribs or the joists, it's about 10 to the power minus 4. Okay, so that was for the joist floor. Let's have a quick look at a demo of a stud wall, which is sort of similar construction. You've got some studs and a plasterboard wall over it. Similar, it's in similar construction, let's say, at least in shape or form, not in material properties, like a timber joist floor. It's just a vertical ribbed structure. Okay. So you've got this stud wall, as you can see. We've got the plasterboard on front. This on the rib. We've got some metal studs on that structure. Okay, so for this stud wall, if you see, so we've got a measured sort of mobility in the bay, center of the bays, and some sort of mobilities we've got over the stud. Okay, and let's see how we can compare this to some characteristic mobilities. Okay, so in the bays, which is the sort of gray line, and if you compare it to the characteristic mobility of a plate of that sort of thickness, you get that dotted gray line, and you can see the actual agreement in most of the low frequency hertz is quite well, even in 1/3 octaves, but even in the extended frequency range is within a decade. So that is very good agreement. And for the stud part, which is the dark red line, you've got also a dashed red line, which is the characteristic mobility of the beam of the equations that we saw in the earlier slides. It matches very well with the characteristic mobility of the beam, and also within a decade in most of the frequency range. So again, an example to show that whatever your structure is, if you use a characteristic mobility as within your design or as a guide, you are very well suited to make some predictions within the building acoustics as sort of a range and building vibration range. Okay, so that's that. This is also, again, the same mobilities that were sort of normalized to the characteristic mobility, and you can see the comparison of sort of the historical sort of mobility master curve for replaced structures on the left, and on the right we've got the same sort of quantities plotted, but for the measured ones, and you can see that behavior still again sort of remaining the same as you can see in the mobility master curve for the structures. So you've got options here. Either you can use the characteristic mobility calculated by yourself, or you can use the characteristic beam mobility to calculate the sort of mobility, estimate the mobility of the stud part. But if you even don't want to go there, you can just utilize the standard sort of values from the mobility master curve, which is 10 to the power minus 3 for the sort of the plate area, which is over the base, and in the rib area, you can just use a nominal value of 10 to the power minus 4. Okay, so with that, I think we've concluded the sort of the predictions, the measurements and the demos. And yeah, if you have any questions, please let me know.
Thank you, Niklesh. There are a few questions actually to pick up. If you
Yep.
want to start with Jalal's comment.
Okay, where were the transducer and impact points on the brick wall? I believe it was over the brick. I mean, Barry, if you want to add, I think it was over the bricks when you did the measurement.
Yes, it's Gary here. It was over the brick.
Yep. Okay. When you characterize the receiver mobility, you should compliant mounting performance as 17 dB attenuation and very compliant. These the long way around. Okay. Let's have a look. Okay. Okay. Compliant machine. Okay, so
I can answer that one actually. Yeah. I think the point that was making, as Nick very clearly said, that there are three terms in the denominator when you have an anti-vibration mount: the source mobility, the receiver mobility, and the mount mobility. If the source and or receiver mobility are very compliant, say like a soft spring, then if you add another soft spring to it, you don't get much benefit. And that's why you get the 3 dB attenuation compared to the situation when you didn't have that AV installed. It's when the source and receiver mobilities are much lower than the mount mobility that you get maximum benefit from the, when the mount and the receiver mobilities are much lower than the AV anti-vibration mobility, that's when you get real benefit from introducing a vibration isolator. But if you're adding a soft isolator to a soft source structure or to a soft receiver structure, you just don't get that much benefit. So the results are the right way around.
Yeah, I think the confusion might have been through the word compliant there as well. In this sort of case, the compliant means the actual your receiver structure is very compliant. It's very free to move up and down. It's very mobile in a sense, so or soft, as Barry said. So if you get very compliant or very soft receiver, you're not going to get that performance or insertion loss from your isolator. I hope that answers your question, John. Okay, so next one from Paul: in consulting as opposed to an academic test, what type of situation would prompt you to carry out on-site mobility tests or predictions, placing a large cooling tower on a thin roof slab? Yeah, so there would be still a couple of questions to answer there. Let's say if you just take your question, you could still maybe say, okay, I would just use some sort of characteristic mobility equations as a first check and see if I can get some isolator which has a far less sort of or sort of far softer than the receiver. If I can get like a isolator which has a lot of static deflection. But otherwise, let's say a situation or a scenario where you may want to predict is, I would consider, let's say, if you have a science and research facility, you have a very critical sort of a degree of predictions to be made for vibration, and you don't know or you are unsure of what your source is going to do, or if you want to check if your source existing sort of source assembly there is compliant with what the design criteria is. So you might want to go on site and do these kind of additional checks and go to the extra degree to make sure all of the sort of things such as receiver mobility are in tandem or are working towards achieving that sort of criteria in sort of supercritical sort of schemes. So I would say that, or otherwise, if you are doing obviously just a R&D test, maybe of some product or some isolator at some site, then you may also want to look at what other systems or the other structure is doing, which is the receiver structure. So those would be a couple of situations I would see where you may need to go to the sort of extra measurement effort to look at mobility measurements. Okay, next one, like my early questions, where would the transducer and hammer points be on the stud wall? On the stud center of the studs, I'm assuming one is trying to measure the response. That would be best to describe. Well, it depends. So if you know where your source is going to be, okay. So if you knew your source was going to be in a bay, I would measure in the center of the bay. If your source had 4 contact points and they would just rightly sit on top of the joist and you were sure they're going to sit on the joist, you can use that. But maybe if you want to be have like a conservative estimate, you would measure on the you use or measure on the bay, because that would be more mobile and that would sort of give you a more sort of conservative answer, because if you just see the mobility of master curve, the bay mobility is generally a sort of a decade or 10 dB higher. So that will, you know, if you just maybe use that, then you know that you've sort of looked at the worst case, because the ribs are relatively bit rigid than the bay. So I would, if I knew where the source was, I would measure there, and in between stud, if it was on the stud, I would measure on the stud. If it was on the bay, I would measure on the bay. Hope that answers your question. Would 30 dB be the upper limit of the insertion loss for an isolator? I would say I've not calculated that personally, but I'll have to see what the most practically available isolator is in the market and compare it with the source mobility. Of course, it also depends on the source, isn't it? So if your source itself, you need to sort of look at the source mobility, as we saw in the insertion loss equation, which was just totally dependent on mobility. And if you had just, let's say, a perfectly rigid base, you still end up with the YI term and the YS term. So I would say it may not be possible to just establish it. We will have to look at what the practical cases are available in the market, what kind of best isolator is available, and what kind of source you're looking at. I think that's from me, if anyone wants to add on that.
That's great. Thank you.
All right.
Yes, if any more questions come in, that's great. But I think what we've tried to do in this first session is some people will be completely new to structure-borne sound power. And so that understanding that you need to understand about your source and your receiver in order to characterize the power that's injected to a structure was one of the main points. The other thing is that today, more or less, everything was shown in narrow bands. So everything that was measured was shown at individual frequencies using FFT analysis. But we started to introduce approximations where we ignored all the fluctuations, so either using simple lump mass spring systems or assuming that the structures could be infinite beams or infinite plates to try and give us straight line approximations. So in the future, we'll be able to move towards prediction modeling where we say, okay, we don't know all this fine detail, but we can make assumptions such that we can move from FFT analysis towards frequency bands, which quite often when we're eventually trying to get to the human perception, we need to work our way towards third octave bands and then summing them up in such a way maybe that we get an A-weighted sound pressure level. So a lot of the time in consultancy and noise control, you're juggling the idea of being particularly precise where you need to be, and then accepting that you have uncertainty either in your understanding of the source or in your understanding of the receiver. And also not deluding yourself that, you know, when cars come off a production line, yes, they've got incredibly good manufacturing tolerances, but there is still variation at some frequencies. So what we try to do is show that actually a lot of the time you won't know precisely where the modes of your concrete floor are, because you never know precisely the boundary conditions. You never know whether the builder included quite the right amount of concrete. So you have to cope with that uncertainty. And as we go through the week, we're going to juggle these two ideas of precision where needed. So we'll look at some very advanced methods in engineering applications with Andy Elliott showing us the train. We'll also think about buildings where we know a lot less about where the source will actually be fixed at the outset. And also there is a great deal of uncertainty due to workmanship and even in the material properties.